In this video, we're going to wrap up our discussion of probability with a discussion of expected value. So when we look at probabilities, we're looking at individual events within the sample space. In other words, individual outcomes of our experiment. When we talk about expected value, we're doing sort of a bigger picture analysis based on all the different outcomes that can occur. So expected value is going to allow us to take these individual probabilities for individual events and determine what we would expect in the long run. So essentially, it gives us a probability-related average if we repeated the situation, or we call it the experiment, many times. So in other words, we're thinking of running the experiment maybe 1,000 times or even 1,000,000 times. Based on some events being more likely than the other, what would happen on average? In other words, from trial to trial, we have different outcomes. But if we run those trials 1,000,000 times, well, how does everything average out based on some outcomes being more likely than others? However things average out based on those probabilities, that's what we call the expected value for our particular situation. So our standard expected value calculation is going to involve 3 steps. So first thing we need to do, of course, is define the sample space. Just define the event we're looking at. What's the experiment? What are the different outcomes? And we need to find the probability of each of our outcomes. Sometimes the probabilities are the same for all outcomes and sometimes they're not. In either case, we need to know what are all the possibilities and how likely is any possibility versus any other one. Then we're going to take each outcome and we're going to multiply the outcome, whatever its numerical value is. All of these ones are going to have numerical values. So maybe the outcome represents a dollar amount, or maybe it just represents just a random number of some type. We're going to take the numerical outcome, whatever that is, and multiply each outcome by its probability. In other words, how likely it is that that particular outcome occurs. And then we're going to take all those products and we're going to add them up. And what that represents, again, is essentially an average. It's how likely is each event versus another. If we were to run this particular experiment in the long run, what's the effect of the likelihood of each event on this experiment as a whole? So for example, let's start with a simple one. Find the expected value for the outcome of the roll of a fair die. So our experiment is taking a single die and rolling it. So we need to start there. That's the action we're taking. That's the experiment at hand. First thing we need to know is what are the different outcomes. We need to start there. What does the sample space look like? Well, if we're rolling a fair die, we know there's 6 different outcomes. We could roll anything from a 1 to a 6. Now, what's the probability of each outcome? Well, the probability that we roll a 1, there's one way to roll a 1 out of the 6 total, and it's going to be the same probability for each of the 6 outcomes. So the probability of each outcome is going to be 1 out of 6 because any roll is just as likely as any other roll. Our expected value allows us to take each outcome. So each of these numeric outcomes, think of the value of each outcome as being the actual number we roll, so 1 to 6. We're going to take each of those numeric outcomes and we're going to multiply each outcome by its probability. And in this case, every outcome has a probability of 1 out of 6. So we're going to take 1 times its probability, 2 times its probability, and so on and so forth, all the way up to our last outcome, which is 6. We're then going to take each of those products, so that's 6 products in total, and we're going to add them together. Now there's a lot going on here. You can do most of this in your calculator, so that's good news. Do not try to type all of that into your calculator in one line. That's a bad idea. It's going to be very, very easy to make a mistake typing something in, and it's going to be next to impossible to determine that you made a mistake typing something in. So we're going to have to think about order of operations here. In other words, based on all these multiplications and all these additions, what order would these operations have to occur in order to adhere to our standard algebra rules? Well, we know that multiplication always comes before addition. So we would need to take all of these products and do the products first. So my recommendation is do each of the multiplications first, evaluate what each of those are going to be, and then you can add the results together. So let's see what that would look like in the calculator. So we're taking 1 times 1/6. We don't need to do that in a calculator. That's just going to be 1/6. Anything times 1 is itself. 2 times 1/6. Well, we can just multiply the numerator. So 2, think of that as a 2 over 1. So 2 times 1 is 2. 1 times 6 is 6. I'm not going to reduce it. I'm just going to leave it as is for now. And then 3. 3 is 3 over 1. 3 times 1 is 3. 1 times 6 is 6. And again, you can do these in the calculator if you need. So 3 times 1 over 6. Just keep in mind, if you do this in the calculator, it's going to go ahead and reduce those fractions for you. But again, it's not going to matter if you just add up all the fractions in the calculator. So if we keep the rest of them, then 4 out of 6, 5 out of 6, and then 6 out of 6. I'm going to add up all of those fractions. So each of these fractions represents an outcome multiplied by the probability of that outcome. Okay, so 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. Now because these all have the same denominator, I can just add up the numerators. So 1 plus 2 plus 3 plus 4 plus 5 plus 6. That's going to give us a total of 21 out of that common denominator of 6. This is the expected value, but what does that really mean? If you take 21 and divide it by 6, you get 3.5. Okay, so 3.5, what does that actually mean? Let's put that in the context of the problem and think about what that means. Expected value means long run average. In other words, if you were to repeat this experiment, which is rolling a die, imagine repeating this 1,000,000 times and then logging what happened each time you rolled. If you were to take all the outcomes from all those repeated experiments and then average out the total, maybe you rolled a 1 here, maybe you rolled a 6 here, maybe you rolled a 2, maybe you rolled a 4, each of them is equally likely, but you have different outcomes on each trial. If you were to run all those trials and then take the average, add them all up, divide by how many trials you ran, whatever average you get is the expected value. What this number means is that on average, you roll a 3.5. Now here's where this is a little misleading. Can you actually roll a 3.5? The answer is definitively no. You can roll a 1, a 2, a 3, a 4, a 5, or a 6. You cannot roll a 3.5. That's not what this means. What this means is on average, because all of these outcomes are equally likely, this will be the average of all of your outcomes. If you take all the outcomes from 1 to 6, each one is equally likely. On average, everything comes out to roughly 3.5. That actually makes sense in this case though, because think about where 3.5 is in this list. It's halfway between the middle two elements. So you roll a 1 sometimes, you roll a 6 sometimes, you roll numbers in the middle sometime. They're all equally likely. So on average, if you were to take all your trials and log everything that happens in the long run, you average out to about somewhere in the middle. But again, it's kind of misleading because you can't really roll a 3.5. 3.5 is just the average of all of those outcomes based on this particular event occurring, or this particular experiment taking place over and over and over again. Okay, let's look at another example. So it's equally probable that a pointer will land on any one of 4 regions numbered 1 through 4. Find the expected value from where the pointer will stop. In other words, if you take this experiment of spinning the spinner and you run the experiment 1,000,000 times, what do you expect on average? We can land on a 1, a 2, a 3, a 4. If we run the experiment over and over, what's going to be the average outcome? Well, we know that these the regions we can land on, we're equally likely to land on all of them. They're all the same size. It's equally likely to get a 1, a 2, a 3, or a 4. So the probability of each is going to be 1/4. There's one way to get each outcome out of the 4 total outcomes. So the probability of each individual outcome is going to be 1 out of 4. So for the expected value, which is our long run average, if we spin 1,000,000 times, what are we getting on average if we average out all of the actual results? We're going to take each value, each outcome's value, and multiply it by the probability that we get that outcome. So 1 times 1/4 2 times 1/4, 3 times 1/4, and then 4 times 1/4. This is basically the same as the problem above algebraically. 1/1 times 1/4 is going to be 1/4. 2/1 times 1/4 is going to be 2/4, and then 3/4, and then 4/4. The benefit of doing it this way is now we have that common denominator. We didn't reduce anything, so we can just add up those numerators. So 1 plus 2 plus 3 plus 4 is going to be 10, and then it's going to be 10/4. And if we plug that into a calculator, that's going to be 2.5. Now again, just like with the die problem, you can't actually spin a 2.5. You can spin a 1, a 2, a 3, and a 4. But if you spun the spinner over and over and over and over again, you logged all of your trial outcomes, sometimes you spin a 1, sometimes you spin a 4, the average is going to be in the middle of this distribution. So you're equally likely to spin a low number as you are a high number. So if you average out all your trials, it comes out to roughly 2.5, which again makes sense because 2.5 is right in the middle between your highest point and your lowest point. So on average, if you take all your trials, the trial results will average out to 2.5. Okay, let's look at another example. Find the expected value for the number of girls in a family with 3 children. Now this is going to be a little bit more involved than just rolling a die and spinning a spinner, but we can take the same approach. So where do we need to start? Well, first thing we need to know is what are all the different outcomes based on the experiment we're looking at. So what's the experiment? Well, the experiment is assigning each child to be either a girl or a boy. So we're having 3 kids. We have 3 kids in this family. The experiment is how are the genders defined. So essentially, what are the different outcomes we can get when we have a family with 3 kids? How can the different genders be assigned? So we need to think about all the different combos. We have 3 kids, and we either end up with male or female. So I'm going to use G and B in this case. So one possibility is that we have all girls. Now I'm going to start with this because we're interested specifically in the number of girls. So what we're focused on with each outcome, each different combination, is how many girls do we have. So one possibility is the first child's a girl, and then the second and third are also girls. So if the outcome we're interested in is the number of girls, that means there's 3 girls in this situation. That's the only combination we can have where we end up with all 3 girls. So there's only one way to get all 3 girls. Now we could have 2 girls and 1 boy. So that could be 2 girls and then a boy. It could be alternate, so girl, boy, girl. Or we could start with a boy and then have 2 girls. Those are all the different combinations where we have 2 girls. Now we could also have 1 girl in our family of 3. So it could be a girl and then 2 boys. We could alternate. Or 2 boys and then a girl. So those are all the ways we could have 1 girl. And then it's also possible that we have none. So we could have a family with all boys, which means we have no girls. So how many different outcomes are there in this experiment of assigning genders to our 3 children? There are 1, 2, 3, 4, 5, 6, 7, 8 total outcomes. So 1 outcome represents 3 girls, 3 outcomes represent 2 girls, 3 outcomes represent 1 girl, and then 1 outcome represents 0. So again, think about what we're being asked. We're interested in the number of girls. So there are 4 different possibilities for the number of girls we could have in a family with 3 kids. The possibilities are going to be 3, 2, 1, and then 0. And based on our exploration of how the different genders could be assigned, the different combinations, that's going to tell us what the probability is for each of these 4 possible totals. So one possible value for the number of girls is a value of 3. Well, how likely is that? There's only one way to have all 3 girls out of 8 total combinations. So the probability of having 3 girls is going to be 1 out of 8. Now, what about having 2 girls? That's another value. There's 3 different combinations that represent having 2 girls out of the total of 8. So that's going to be a probability of 3 out of 8. Now, there's also 3 out of 8 possibilities for having 1 girl. And then 1 out of 8 is the probability that we have no girls. So the value in that case would be 0, because again, the value we're interested in is the number of girls. It's got to be a numeric value. You're going to find as you do expected value problems that you're going to have to be a little creative sometimes, because if we're thinking about outcomes as being combinations, well, the combinations themselves are not numeric. They're just orders for G and B, if you want to think of it that way. We have to find some way to interpret all of this numerically. So we're interpreting this numerically as each outcome representing the number of girls in that outcome. So there's one way to have 3 girls, there's 3 ways to have 2 girls, there's 3 ways to have 1 girl, and then there's 1 way to have no girls. So that gives us all our probabilities. We're going to take the products. So 3 times 1/8 is going to be 3/8. 2 times 3/8, that means we multiply the 2 and the 3, and we have a denominator of 8, so 6 out of 8. 1 times 3/8, 1 times 3 is 3 out of 8. And then 0 times 1/8, 0 times 1 is 0 out of 8. We add up our numerators. So 3 plus 6 plus 5 plus 0 is going to be 12. And then we have that common denominator of 8. So 12 out of 8 is going to be 1.5. Now, can we have 1.5 girls in a family? No. Each child is either a boy or a girl. The possibilities in the sample space, remember, were 0, 1, 2, and 3, because what we're actually interested in is the number of girls. We cannot actually have 1.5 girls. But if we were to look at a bunch of families with 3 children and average all of the numbers of girls, some families will have none, some families will have 3, and it averages out to that halfway point at 1.5, just based on the probabilities we have. So the expected value of the number of girls, that long run average, if we were to look at a bunch of families with 3 children, in other words, run the experiment multiple times, would be about halfway at 1.5. So just to sum up this whole idea of getting the expected value and interpreting it, it may not represent a possible outcome, particularly when our outcomes are exclusively whole numbers. So if we're averaging and then based on dividing, it's the division that gives us a problem. We're dividing to take an average, but anytime we divide, we run into the possibility that we end up with numbers that are decimals. If our actual outcomes are whole numbers exclusively, then once we divide, we run the risk of running into something that can't represent an actual outcome because it's a number that's going to have a decimal attached to it. But again, we're not looking at potentially a possible outcome. We're just looking at the long run average if we were to log data from a bunch of trials of our experiment and then just average out the outcomes that we get. So let's put this into application. We use expected value a lot, or a lot of situations we apply expected value. Let's look at some of the different situations where you can apply it. So one application is going to be risk-benefit analysis, which insurance companies and business ventures may use to determine whether or not it makes sense to make a particular decision, just based on what you expect to happen in the long run on average. So it's going to require the determination of empirical probabilities, which are probabilities that aren't based on theory. They're not based on just a conceptual analysis of a particular experiment. They're based on actual events and actual data based on past occurrences. So we're still going to have numeric values to our outcomes. We have different outcomes based on our situation, and each outcome is assigned a probability. So let's look at an example. So an automobile insurance company has determined the probabilities for various claim amounts for drivers aged 16 through 21, and we've got all of those values in the table below. So we have claim amounts ranging from 0 to 10,000, counting by 2000s. And then we have the probability based on what this company has seen in the past. So how were these probabilities determined? Well, they looked at past results in terms of how often different claim amounts popped up. How often did a claim amount of 0 pop up? How likely was a particular driver to never have to make a claim? That would be a claim of 0. This was how likely it is, so they estimate the probability just based on data they have from the past. $10,000 as a claim. They looked at how many people had roughly a $10,000 claim. There weren't that many, so they estimated the probability of that happening in the future to be low. So they're just basing the probability on data, how many times they saw this occurrence based on how many occurrences they looked at. Was it likely to happen? Was it unlikely to happen? Okay, so we want to know what is the expected value, and we want to describe what that means in practical terms. So let's look at the actual table again. So here are our values. The expected value of this situation is going to be each of the values multiplied by their probabilities. So we're going to take each of those, each of the numerical values, the dollar amounts in this case, and multiply each by how likely it is that that particular outcome occurs. Okay. So I've gone through and done all of this. Take a minute, check it. You might want to pause the video and make sure you can do all of those. Do each product in your calculator, and then you want to take the sum at the end. So notice a $0 claim has a 70% probability, but that still comes out to $0. So it doesn't actually add anything towards the total. And then we have those other subtotals based on other claim amounts and how likely or how unlikely they are to occur. If we sum up all of this, it sums up to $1,100. This is our expected value. So what does that mean? That means in the long run, if we look at driver to driver to driver, maybe a million different drivers that fit under this category, and we average out how many or how much money is applied towards a claim for that particular driver, it's going to average out to $1,100 in the long run. Now, some individuals may never make a claim. Some individuals may have to eventually make a really large claim. But if we average out all the totals for a lot of people, it's going to average out to $1,100. So what they're going to use that for, what the insurance company is going to use that for, is as an estimate. They can't determine from individual to individual how much that individual is going to require in terms of a claim amount. They don't know. Officially, someone could have no claims or they could have a really large claim. From individual to individual, you don't know. But this is what they expect to be the long run average. So they're going to plan for that much for each individual they sell a policy to, just because this is the average that they expect in the long run. So what does that mean in terms of the next question? The next question is, how much should the company charge as an average premium so that it does not lose or gain money on its claim costs? So the premium is how much they're going to charge you in order for you to subscribe and to get the benefits. Well, if they expect the average claim to come out to $1,100, this is the average claim amount over a long-term analysis. If they want to break even, in other words, they're charging you so that they plan on not losing or gaining, then they would charge you exactly $1,100. If they expect $1,100 to be what everyone needs on average, then by charging everyone exactly $1,100, then they expect to, in the long run, neither make money nor lose money. Now, because that means that's the average and that's what they expect on average for every individual who makes a claim, that means they're probably going to charge you more. So if they charge you more than $1,100, they expect a profit. Now, again, from individual to individual, say you make a $10,000 claim. If they charged you $1,200, well, they have that $1,200, but then they had to pay out $10,000. So did they make money on you? The answer is no. But as the long run average, if you look at everyone and average out everyone who doesn't require any claim and who does require a large claim, it averages out so that they need $1,100 per person. So if they charge more than $1,100, then in the long run, on average, they will make money